say stay cool in windowless fans?
Say what, bro?
Does it say stay cool in windowless fans?
Does it stay cool in
Windowless fans.
vans with no windows?
Yeah.
Pretty much. Especially there's little air movement. I can imagine that, like, as an ER doctor. That's all I got. I'm here. Yeah.
In front of when it says humans add, and it says, is that 0.50 or is that plus?
Plus. I guess they're all additions, so you can take off the plus.
What does it say for gases?
If there's something you can't read, we'll go over it. Raise your hand if you need more time to tape it. some solar house model time in the class on Wednesday. I have a field trip with VADA on Wednesday the 11th. I think I told you that the plan could change. It's changing on Wednesday the 11th. You'll have the last few study goals in the unit. There's like a second movie for 30 minutes. And then that'll leave you about 20 minutes to work with your solar house groups. But you should know Wednesday plan is changing. Bring your plans and whatever you got to work out with your crew about how to put stuff together. How many of you have made a cardboard mock-up of your house other than Mackenzie Bell? What? I don't know. Good. Because I already knew. Cardboard mock-up. If you haven't, I would strongly recommend you do that tonight, or in the worst case, Tuesday night. So you'll have something to work from when you meet with your group on Wednesday after the meeting. Keep in mind that you're, like 2 weeks away from the solar house model being due. So given the time it takes to put together thermal mass, I think I'm shocked that only 2 of you have made your cardboard mock-ups. You should really get on that. All right. I'm not shocked. I understand. All right. Did we finish talking about this last week?
Yep.
That's good. Because today, I want to finish what we know about climate. Then I want to talk about how the greenhouse effect works. And then I want to talk about climate change. These are like the final steps in our conversation. Did we talk about how we know the temperature in the past?
Yep.
Yeah.
We did? We talked about the layers of gases trapped in snow?
Yep.
And did we talk about the sediments at the bottom of lakes? Okay. Please look up. This is Africa. And these are the Rift Lakes. And look, that skinny long one is this one. Lake Tanganyika. And that's an extremely old lake. It is one of the oldest and one of the deepest on the planet, which makes it a really good way to find out past temperatures. How the hell would we know the temperature based on a lake?
It's older than you?
How?
Sediment.
How does the sediment tell you temperature?
If it was hotter in the past, the lake would have been less, have less water in it. So,
Yeah, more snowfall maybe, yeah. So we can kind of tell the water flow rate, but the lake is really deep, so when it's really hot or it's really cold, there's still some water around. What else can we know from sediment?
The color.
Yes, but how would that help us? How do we get the temperature of the Earth by looking at sediment? This is a pretty, aha moment. I challenge you to try. Imagine I can give you this. You can use carbon to tell how old the sediment is, so we can date the sediment. How would we know temperature based on layers of sediment?
Maybe like different years, it would permit more sediment or less sediment to sink to the bottom in different kinds.
There are definitely those patterns. I am not convinced yet how that gives us temperature. I mean, we can get temperature down to fractions of a degree, like 18 million years ago or whatever. I mean, not 18, like 8 million years ago? How?
Maybe like what type of life was it living where? Like different things living in different.
So what would show down there?
fossils, and you would also use more evaporation would leave more sediment and other kinds.
The thing about the sediment evaporation flow rate stuff is that would not give you very accurate temperature records. But the different animals and different life and different, now we're kind of getting somewhere. Anybody want to raise your hand? Is that you? Is that what you were saying? There's one type of life that can tell you very exactly what the temperature was. What?
Algae?
Close. Yeah. Further. You look in the layers, figure out how old they are. Anybody know what those are? You with me?
Yeah.
What?
Do you have tap water and paperclip?
Tap water maybe in my fridge.
Okay.
If not, you can fill up with that from any tap. There's
Okay.
a tap right outside the building here.
All right. Well, check your fridge first.
Sure.
Do you have paperclips?
Yeah. Anybody know what those are?
See one, thanks.
There. Really, nobody knows what those are. What are those named? What do they end in?
You know algae?
Zooplankton?
Yeah.
Fungus?
Plants each have distinct pollen.
Oh.
The shape of pollen is distinct, like keys in a lock. No female plant wants to pick up pollen from the wrong species. That's a waste of her energy. No male plant wants to pollinate the wrong species. That's a waste of his pollen. So plants each have very unique pollen morphology. And there are nerds who can tell. You give somebody a snapshot of 15 different pollen samples, and they can give you the temperature very exactly. Because look, let's say that palm trees have that temperature range, and orchids have that temperature range, and wheat has that temperature range, but sunflowers have that temperature range, and then I'm running out of plants to make up. Cycads have that temperature range, and all of a sudden you can see that each time we've identified a plant, we narrowed our spectrum of temperatures a little bit, right? If all 5 of these plants existed at the same time, the temperature has to be between this and that to include all of them, right? Does that make sense to everybody? It's called archaeolimnology or paleolimnology to find records in lake sediment.
How do they know that, like, say, like, palm trees today have a certain temperature range, but how do they know that it was the same back then?
It's kind of speculation, but for many plants, we've seen their fossils. You know, plants go back really far. Compared to the rest of life on land, plants are like way more than all the other life. So we have a pretty robust fossil record, and we assume that if their morphology hasn't changed at all, they couldn't make a living too differently than they make a living now. So there is a little bit of fudge factor here, I think. But it gets a lot more convincing when you've got 20 or 30 or 80 or 600 plant species in your sample. Yeah. This can be calibrated by other forms of life, like somebody said algae, and you can calibrate that with like bacteria and insects. And when you add it all together, you get some really, really, really accurate temperature records because we know each species' temperature tolerance. Is nobody else impressed by that? Like that concept? That just seems so cool to me. I think that's so neat. That nerds can look at the sand and be like, yeah, its temperature was 73 degrees. I don't know. I find that really neat. When you put all that stuff together, we know some things. About 15 or 20,000 years ago, we were in an ice age. About 9,000 years ago, our global temperature started to reach a pretty warm period. For the last 8,000 years, we've been roughly, dropping in temperature. That little blip is the last century or so. Almost all, the line is too thick for you to get a lot of detail. But technically, almost all of that jump at the end, almost all of that has been in the last 15 years. I hope there's a few things that stand out to you. One of the important things that everybody has to know is the planet has been hotter than today. But the planet has never warmed this quickly, including the volcanoes and meteor strikes that caused global extinctions in the past. It's never warmed this quickly. We used to have pretty good records for a few thousand years. We can now go 12 or 13,000 years back with less than a half-degree accuracy for any decade. We have 0.4 degree accuracy decadally for about 15,000 years. And we have roughly the same, I believe it's either 0.5 or 0.6 degree accuracy for century averages, going back hundreds of thousands. And the jump that we've made in the last few years is completely unprecedented in any place we can look at temperature records, as far back as we can look. It just doesn't jump that much. Yeah?
How do we know our accuracy if we don't know the actual temperature of those?
Well, you know how much guesstimation there could be before you reach temperatures that could not be. Like, the temperature wasn't this, and the temperature wasn't that, so you can rule out what's possible and then what's impossible. That's your fudge factor. So it's within parameters of accuracy. I also want to remind you about our climate models. Remember that thing about predicting the past with the computers and stuff in the movie? We used to have really simple climate models. The more we learn about climate, the more we add. So those ocean circulation currents, how much ice there is and how much that reflects and where the clouds are and what's on the surface of the land. And we've added so many variables. We now have like atmospheric chemistry, we have terrestrial chemistry, we have the gas interactions of vegetation in different parts of the planet. I mean, there are layers to these models now that would boggle your mind in their complexity. And remember also that computers have gotten smarter, so instead of calculating the planet as a few big blocks, we can break up the planet now into trillions of little itty-bitty blocks. And we know how they interact with each other. Our computer models are getting smarter. And we can test the past against our temperature records to make sure that our computers understand what's happening. The light blue is what all natural factors tell us about climate. The pink is if we add human factors, and the black line is our record of temperature. In other words, nature can explain the past. Nature alone cannot explain the recent jump in temperatures. Nature plus humans does explain the recent jump in temperatures. If you roll these forward into projections of the future, even if you assume humans disappear from the planet today and we're not adding any more CO2, that's the bottom one. Any way you project these trends into the future, the planet's going to be getting a lot hotter. This is what we mean how there is no scientific climate scenario where global warming is not a thing. I'd like to quickly do number 19, or number 19? Yeah, number 19 just happens to be in the way. One quick one. Why is there an annual up and down to global temperature? To global CO2 levels? Yeah, it's kind of seasons, but
Plants.
how is it seasons? Yeah. Plants do take out CO2, but wouldn't the northern hemisphere summer be the southern hemisphere's winter and vice versa? Don't the seasons cancel each other out?
No, because there's more land mass in the northern hemisphere than on the southern hemisphere.
No, because there's more land mass in the north, so they don't cancel out. But anybody know the other side of what Hooke is saying? Because it's not the land mass, it's the inverse.
Water.
It's the ocean, the water, because algae soaks up all the CO2 and makes all the oxygen. So when it's a southern summer, the planet's CO2 goes into algae. And then, in the southern winter, when those algae die and the CO2 builds up in the atmosphere, there's not enough ocean in the north to soak up all that CO2. And land barely does photosynthesis compared to the ocean. Yeah?
Wait, so in the summer there's more algae in the ocean in the northern hemisphere?
No.
South outside.
The southern summer has more algae. The southern summer has more algae. So global CO2 goes down.
More algae is less CO2, right?
More algae is less CO2 because algae does photosynthesis. They eat CO2 and they make oxygen. Keep in mind, I'm just talking about the rhythms up and down annually. The global trend in CO2 should also be obvious, right? The long-term trend. That the line is effectively going uphill. Okay, but that part was easy. Can anybody explain to me the car lock thing real quick? Yeah.
Light goes through the window, and the light is transformed into heat energy as it hits the car's dash and everything else that's inside the car.
Interior.
The interior. But then the heat can't escape through the windows, so the entire car heats up.
That's pretty much bravo right there, yeah. What else just said? The light goes through the windows, is absorbed by the interior, is transformed into heat, and the heat cannot leave because the windows are closed. Right? Everybody got that? How could you make your car cooler? God, I can't speak. Yeah. You open the windows, let out the heat.
But how does that relate to the greenhouse gas? Like, is it like those ozone holes? Is that like
I promise I'll show you, but don't say ozone when you talk about greenhouse.
that's sorry.
Yeah.
Well, having the windows open up is like adding more greenhouse gases. Those windows are down, so coming off through greenhouse gases because the heat can escape.
So that kind of answers you that the windows are like the greenhouse gases. How much heat you keep in, how much heat you let out. Agreed? But let's keep going real quick. Let's keep going because there's a couple other things we could do to that car. What else could you do to that car? Anybody have tinted windows? How do the tinted windows help you out?
Block the light.
They block light. So does your interior warm up as much? Anybody experience this? Been in like a really shady car, fancy limo maybe, something? Yeah.
You can have a lighter color interior.
That's right. That's right. When my wife and I bought her Subaru, we got the lightest we could get, which sucks because it's still almost all black. But, yeah. And so here we have it. All of the variables have been included in this conversation of car temperatures. And I really do want to make sure we all agree about the car thing, because I'm going to rely on this later. Windows up or down trap more or less heat. Window tinting keeps some of the light out, or in the absence, lets more light in. Interior colors transform more of the light into heat if they are dark, less of the light into heat if the interior colors are light. Agreed? Everybody with me so far? Are we cool with all this? Yeah.
Does exterior color change anything?
In a real car, it does. In our analogy, that factor is essentially moot. If you're curious, in a real car, a black car absorbs more sunlight on the outside, and that temperature translates through the metal, radiating back into the interior. And to a small degree, our atmosphere does absorb some light and radiate heat back down on us, so maybe that's not irrelevant. Yeah. Look, if you don't understand cars, maybe you understand greenhouses, which are built with the exact same variables in mind. There's glass, so light comes in. Remember, that's ultraviolet. Get your energy right. And that energy is absorbed and given off as infrared or heat. If you close all the vents, you get a hot greenhouse. That's what greenhouses are for. Yeah?
So are we talking about the heat as being like radiation, or is it, in the air, or is it both?
I don't understand the difference, but yeah, I mean, it is radiated from surfaces and absorbed into stuff in the air. In a vacuum, that heat would not be heating any air, but because there's air here, we are heating that air. No?
Sure.
So look, light comes in, heat either escapes or is trapped, depending on how much you're trapped, how many vents you have open. Right? If I paint the outside of my greenhouse, I can bounce out some light so there's less heat being made on the inside. James Mel, if you're using a phone right now, I swear to God, Bobro will strangle you. Bobro, kill. Sick balls. Get it. Get it, Bobro. Daisy O'Mahony will crush you.
Yeah.
That woman's like 100% muscle, like a shark.
Pretty much.
Pretty much.
Crush skull between thighs.
What? I don't know what you're talking about. But please put your phone away, James Mel. No, don't cover it up. Please put it away somewhere further from you. Thank you. All right. So we got our greenhouse effect. Does anybody know how greenhouse gases do that?
It's basically like how much glass would be on the windshield.
That is what, yeah. So more greenhouse gases is more window rolled up, trapping more heat. But this is one of the common myths. Remember I told you I've got a chip on my shoulder about people who raise objections to climate science when they say stuff that is not accurate? So one of the things that people say is, you can't even explain how greenhouse gases. It's like, yes, we can. Anybody know how that works? Look, first of all, we all agree on a greenhouse, right? So some amount is scattered, some amount is absorbed, becomes heat. Might be easier to see in this one. Light bounces off, sunlight is absorbed. Of the light that's absorbed, heat is given away. Most of the heat escapes. Some of it stays. That's the greenhouse effect, the heat you keep, the extra heat. Does that make sense to everybody? The trapped heat? Yeah.
So how is it trapped? Like
How is it trapped?
Or the clouds? Or like,
If I mean, metaphor for a minute, analogy for a minute. If I said window trapping heat, you'd understand? Yeah or not?
Yeah.
And if I said vent trapping heat, you'd understand? Right? Because that heat wants to rise away from the heat source but cannot escape, and so you're just trapped with all your heat. Right? Okay. So how does the atmosphere do that? How do gases trap heat?
If they absorb it and reflect it back to us.
Pretty much, yeah. They absorb it and then they give it off, and most of that comes, and some of that comes back to us. They give it off in all directions. We get about half of it. Yeah. Watch me. This is the dorkiest demo of the year, but it's all I got. H2O. Right? 2 hydrogens and an oxygen. I get a headache on this day. Everybody understand what I mean, right? I got my 2 hydrogens and my oxygen. Yeah? Water. We good? Now, maybe somebody understands chemistry well enough to explain the hydrogen bond. That's like a couple of, that's like a shared electron, 2 shared electrons, something like that. Well, hydrogen has 1, oxygen needs 1.
So it's just one electron.
So there are, well, 2 switching places, basically. There's 2 between them. One of the oxygens is being used by the hydrogen, one of the hydrogen is being used by the oxygen. So, right? Everybody understand that? Do you all understand that? Yes or not? Okay, now here comes the fun part. No. This is the part you will need to know. That bond, which is shared electrons, can be heated. You give it heat energy, and those electrons, they move more. Everybody understand that? That when you heat up a molecule, you can heat up electrons, they'll move more? Everybody, yes? We good with that? So watch me. When you heat up a water molecule, a single water molecule, it gets, this is a science term, wobbly. That's a science term. By the way, there are terms for the different types of wobble. There's this type of wobble, and there's this type of wobble, and then there's this type of wobble. And there are others, I don't really know them. It was in one of my chemistry classes when I was in college. I learned the different types of wobble, and I could draw them for you, but I've forgotten. If you want to look it up, I'm sure it's on your Google machine. Molecular bond wobbles. And so watch me. You heat up that water, and over time, those electrons, they want to come back to a more rational energy level. So over time, that water molecule will give off its heat, and those electrons will restabilize in their movements. greenhouse gases. They absorb heat into the bonds, and then when those bonds stabilize, the heat is dissipated back to the atmosphere. Yeah?
So what is the difference between a greenhouse gas compared to a regular gas that's not a greenhouse gas?
Not all gases do that. Some gases have different types of bonds, or sturdier bonds, or there are other molecules which might just break up given energy, right? But there are a few, mostly these, that can absorb a certain amount of heat. They don't all absorb the same amount. If they have really strong bonds, they can take a ton of heat. And eventually they restabilize and give off a ton of heat. Yeah?
Is more heat given out or is it the same?
No, they absorb more heat, so they give out more heat. It's like they can store more energy in their bonds. Yeah?
That doesn't really make any sense.
Okay, how do I explain this better? Go ahead.
So, the light coming in from the sun is absorbed by the greenhouse gases?
No, by the land.
So then it's the...
Re-radiated heat energy.
that then gets... Is it getting reflected from the atmosphere on the outside, or is it getting
No.
absorbed?
Absorbed into greenhouse gas bonds.
And then the heat that comes off of that goes, like, back to the Earth?
All directions, but about half of it comes back to the Earth, yeah. Does it make sense?
No, it makes more sense. I thought it was the incoming radiation. It wouldn't make sense.
BT dubs, there is a little of that too.
Yeah.
So some incoming radiation does become heat in the atmosphere directly. The part I'm not clear on is whether that is in the greenhouse gases themselves, in other gases, or in particulate matter in the atmosphere. You understand what I mean by that? The amount of light that's absorbed and made into heat in the air, I don't understand how that transformation happens.
Yeah, and also in the book they said that like particulates, like aerosols, they actually reflect light, and so they like not contribute to global warming. But I didn't really understand that because we have an aerosol problem. So
There may be two problems with aerosols. The heating problem of aerosols is not the particulate. So there are aerosolized particulates, which is things moving, and then there are the aerosol propellants, like the chlorofluorocarbons, that fire those off, and those gases are the ones that bubble. Notice they have fluorine and fluorine and super strong bonding, so it can absorb unbelievable amounts of energy without letting go. Anybody else have questions for me? I hope I'm making sense. I've noticed that period 2 is exceptionally sleepy today.
Why do you...
Time change! The time change! All this time I was judging betters. I fell asleep for period 0 today. Makes you feel any better? I had to cancel class. I woke up at 7:01. I had to be there at 6:50. But back to the real life. Look, I'm sorry, but I really do need to make some points today, and you do need to do some writing, and the learning must continue. First of all, you understand this, transformation, absorption of ultraviolet, giving off heat. You also understand some heat leaves, some heat stays. The secret that people have never taught you is that gas molecules can trap heat, and then when those bonds restabilize, the heat is re-emanated. Those are the greenhouse gases. Now what you need to know and get ready to write real quickly. There is a natural greenhouse effect. That's why you're glad you're in the on Earth and not on Mars. On Mars, there's no atmosphere to block ultraviolet, and there's no greenhouse gases to keep your heat. So without an atmosphere to block ultraviolet, Mars doesn't have this. All the light hits Mars, so Mars gets to 300 degrees at the end of the day. Because it's had unfiltered ultraviolet. And then separately, Mars has no greenhouse to trap the heat, so as soon as you get to the dark side of the planet, there's this dramatic heat loss, where it drops to 200 negative in a matter of minutes. That's why Mars is so windy, because there are such extreme temperature and thus pressure differentials on Mars. Yeah?
How hot do you think Earth will be when our atmosphere is completely depleted?
The funny thing is, our atmosphere will never be completely depleted. If anything, we're just adding more. Separate, I don't know that that has a logical endpoint. Theoretically, we've got a lot of fossilized carbon we can turn into CO2. So I don't think we'll ever get to that point. But if we were to actually hammer all the carbon and put it back into, I mean, we might run out of oxygen. Get close to that. And our planet can theoretically get super effing hot. The other stuff we're adding might heat us up even more. I don't know what the end point is. I can't imagine a number to answer your question with. Yeah?
So you said that Mars didn't have an atmosphere?
It has a very thin atmosphere.
Okay, so that's what it is. It's like where, like, there's some gases?
Yeah, yeah. Who else? Yeah.
How long does it take for the greenhouse gases to turn it into heat?
I don't know. That's a great question. I'll bet you it's an ongoing
fast, or
process.
is it like-
I'll bet you it's an ongoing process.
Okay.
But yeah, I would imagine it's a full, like, an immediate, like,
Yeah.
those bonds will start to stabilize right away.
Okay.
You know, like a spring that's been made to wobble. As soon as it can, it'll start to.
Okay.
All right. These are 1, 2, 3, 4, 5 naturally occurring greenhouse gases. If you measure their share of the natural greenhouse effect, most of the greenhouse effect comes from water. And there's not a lot of CO2 in the air, but what is there is responsible for a good bit of the natural greenhouse effect. There is some variation there because of seasonal and situational variation. So we get a little bit from methane, nitrous oxide, and ozone. That's lower ozone. That's ozone down by us in the troposphere, not up there in the stratosphere. That's down here. Little bits of ozone down here. Yeah?
Where does the ozone come from?
The same sort of reactions that make it up high will more rarely, but the same reactions make it down low. So a little bit of ozone is naturally built even at the bottom of the troposphere where we are. Humans also add quite a bit of ozone through human activity.
Like what?
Electronics, EMFs. So it's not like I'm worried about EMFs giving you cancer, like brain waves and the tin hat stuff, but EMFs do split oxygen, and those lonely oxygens will often cluster onto an existing double of oxygen to make O3.
This might be a little off topic, but how come you can feel a temperature difference when you're like on the ground when a cloud goes over the sun like instantly, or like it's 8 minutes for the solar radiation?
I'm not sure what you're feeling, but you're probably just feeling that, I don't know.
Wait, when the cloud goes over the sun, you just don't get light.
I mean, the cloud's a lot closer to you than, you're not blocking it on the sun. You're blocking it here.
Yeah, I was thinking.
Yeah, so of those 8 minutes, the light's already spent 7.59999 before it hits the cloud. Next, please consider there are no fluorinated gases in nature, and we'll talk about those soon, but they are major industrial greenhouse gases. We'll come back to that. Also consider that humans add mostly CO2, methane, nitrous, a little bit of ozone, and all of those fluorinated gases. And so, if you want to figure out the percentage of the human effect, CO2 causes about half of the human effect. Methane causes about 12 to 20. Nitrous and ozone a little bit, and fluorinated gases a bunch. Yeah?
Wait, on the CH4, when it says humans add, does that say like 140 plus 50%, or was that?
140 to 150. How about this? Hold on. Let me write this differently for you. Humans add roughly 150% more. We've more than doubled methane levels. And
is that just like from natural gas coming out of us, or how do we increase the methane?
Cows.
well, we do a bunch of stuff that increases methane. So if you add it all up, and methane lasts a long time, CO2 has like very rapid biological integration, but methane does not. So we have added a lot of methane from anaerobic decomposition of various sorts. Some amount of like farm debris being left on the surface adds methane. The livestock adds a lot. The landfills add a lot. The changes to wetlands have added a lot.
And from natural gas too, not burning it.
Yeah, and leaking gas. Yeah, absolutely. Absolutely. What I do want to point out to everybody before the end of the period, though, is this stuff. This says fluorinated gases, which are also known as the industrial greenhouse gases. FLUO, yeah, fluorinated. 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 Here's the fun fact about those. They don't exist in nature at all. They're used entirely in making microchips as coolants. And generally speaking, in a number of weird industrial processes, like making styrofoam, drying fiberglass sometimes, working with silica, like microchips. And those industrial gases, please look up halon CFCs, sulfur hexafluoride, hydrochlorofluorocarbons, and perchlorofluorocarbons.
Is that PER, POR?
PER. Those get really hot. They can hold a lot of energy in their wobble. In other words, these are gases that are entirely non-existent in nature. Some of them are extremely stable, and they get extremely hot. If you don't mind, I want to point out one last thing before I go on with my slideshow. Please look up. This is not a chemical formula. That's not a chemical formula. See how it says C dot, F dot, C dot? That means chlorinated fluorocarbon. So the chemical formula would be 3 chlorines, a fluorine, and a carbon, for example. And there are many ways to do that. There's a lot of ways to hold those pieces together. So we call it a category of fluorocarbons with chlorine. And those can include hydrogen, and they can include other stuff. Yeah?
Where do we get CFCs from?
We make them.
What do we make them out of?
Chlorine, fluorine, and carbon.
So where do we get fluorine from?
The supermarket.
Baby Jesus?
Yeah, I mean, this is the glory of industrial chemistry. Like, almost all of this starts, like, the carbon is usually from natural gas or from naphtha. The fluorine, I don't know how to purchase fluorine, but it must be something that, mining it or gas? I don't know. Mining probably? I don't know. Do we mine it? And the chlorine, I don't know. Yeah.
Since we invented one of these gases and that wasn't naturally occurring, is there any way that we could like accidentally invent something that just adds a ton of carbon to the atmosphere and just destroys it?
Well,
I mean, if you're thinking the kind of volume that would take, probably not. But yeah, the point is we had no idea the climate implications. I guess there must have been a chemistry nerd that could have put that together, but I don't think that was part of the consideration when we started using them industrially. No, that wasn't part of it. So look, I want to show you guys something really quick. First of all, from the 70s until a decade ago, every kind of greenhouse gas has gone up, except for water. In the last decade, CFCs have started going up again, carbon has really taken off, and methane has really, really taken off. And the wacky thing is, none of this has any sort of cutting-edge, questionable scientific placement. For example, the first person to talk about how climate is affected by gases did so in the 1820s. And the first person to do experiments about how extra gases in the atmosphere would cause extra temperature on land did this in the 1850s with homemade labware because you couldn't buy glass stuff. People were already talking about fossil fuels changing climate when my dad was a baby. It was in the New York Times. Like, you can go to the old public libraries and get a copy of a 1959 paper where this guy talks about how he wants to start a project in Hawaii to start measuring gases. This is the man that drew this line that you looked at earlier about the earth breathing. Notice he started recording in the 1950s because everybody saw this coming. The conversation we're having today about like the questionable, oh, I don't know about climate science is totally fake. It would be like people convincing you that the earth might be flat after all. You got to be a real sucker to fall for that. You got to be a real sucker to fall for that. Remember, it's not just the CO2. Keeling saw the CO2 going up, but nitrous and methane have also been going up. And look at that curve shape. That perfectly matches our temperature records. And no matter what, everybody keeps talking about waiting for evidence. How about ocean heat since 1950, changes in sea level, the amount of energy stored in different parts of the Earth, Arctic temperatures in the last 2000, Arctic ice pack going downhill, Arctic ice mass. Look at that drop. How the North Pole is running out of ice just recently. We can look at the rate of Greenland melting. We can look at the overall mass of Greenland. The ocean conveyor belt spot. Remember we talked about that. Global average for the last 160, or for the last 11,500. I can't believe that people talk about, like, I don't know, I'm not really clear, there's not enough evidence, show me the evidence. Like, okay, it's called the Google machine, we'll get you all the evidence you want, it's been published for a long ass time. Oh, and people want to talk about the scientists who don't agree. Let me show you about the science real quick. Sorry, I can't remember how this was supposed to fit into my lecture, but it's funny. So, people talk about the Dow. So, 11% of scientists from any field dispute climate, and of climatologists, 1%. This is looking at a survey of 10,257 Earth scientists, by the way. And that was just one study. Here's a different study in 2009 and again in 2010. This is how you look at it if you ask them. In all these different studies, each of these colors was a different research project asking scientists. So 2011, 2010, 2009, 2008, and 2007. So do you think it's largely caused by humans or by other stuff? That's your disagreement right there. And by the way, there's been research that a lot of these guys have been getting paid by the energy sector. But the media doesn't help. Look at this. Here's your media coverage. With humans primarily causing in green, and humans not primarily causing in red. That's your media coverage. So at the bottom, look at your public perception. With humans causing climate change in green, and humans not involved in red. Notice how media guides public opinion, not science. None of this is disputable. Those basics, find me any credible science. We can talk about how predictions of the future are hard to agree with, but none of this is disputable. You got to be able to say all that. We'll start here tomorrow.